All right, welcome to December. What questions do we have for a new month?
I have some questions about the project 4, or should we wait until lab for that?
Yeah, we'll probably wait till lab to talk about that stuff. Yes, the final is cumulative as well. What other questions do we have? A little over 2 weeks to go. All right, parity. Parity bit is going to be foundational to other things. It's used in a few places. Right, so it's used for error detection and correction. Some schemes. Right, so parity bit is a single bit. It is added to a data payload to help identify if there is an error in the data. And so there is even and odd parity. Our options will stick. When constructing a message, the way it works is we'll count how many on bits there are in the data payload and then add in a single bit for parity. If the count of on bits is already even, we'll set the parity bit to 0 to keep it even parity. If the count is odd, we'll set it to 1. Make parity even. And so if our data bit was 0, we would have even parity at that point. So we'll set the parity bit to 0, and the bits that we would send along would be 0, 0. If we have as data a single bit, usually there's going to be more than one data bit. We're starting at smallest examples, right? So that's an odd count. Add in an additional even, and now we have an even number of on bits in the total payload that we're passing along there. Right, we had 0 on bits, that's even, so we'll keep our parity bit 0. 0, 1, 1, 0 doesn't matter. Oops, get ahead of myself here. We have 1 on bit, 1 being odd. We will set the parity bit to 1, and then our total payload has an even number of on bits. All right, so when we look at the final payload, we count the number of on bits. It should be even after counting for the parity bit. All right, growing in the number of bits. Doesn't much matter where that one bit is on. That's an odd parity. They have only a single bit on, and we want to make the whole thing even. So we'll set our parity bit to on, giving us an even count of parity bits. Everyone with me here for the pattern? All right, so the payload might be quite numerous, the number of bits in it. But if it's already even, we'll leave it as such. And we'll group them in nibbles or bits, blocks of 4 bits, make it easier to read whatever it is that we're, you know, whatever it is we're working with. All right, so we'll look at all the bits in a particular packet or chunk or block or whatever you want to call it. Count them up. If it's an even count, then things are good. All right, so using a parity bit for error detection. When reading a block of bits sent to us, we'll check the parity of that block. If the parity is even, we presume that there isn't an error in the payload. Parity is odd. Type that is even part here is odd, and we'll suspect data corruption. All right, so we can take the same table and do some data corrupting. All right, so for a data block was 7 bits, say we're just doing lower or upper ASCII, lower, upper, I forget, whatever, the 7-bit part of the ASCII table where alphabet is and most of the other common symbols. And then we're passing along an extra bit there to make sure that our data is intact. Let's see, is the purpose to be even? Why is 3 all bit allowed? Is that only num that is allowed? It's not the number of bits. The number of bits that is the payload is arbitrary. It's the number of on bits that we care about and whether that number is even or not. All right, so there's a lot of different ways that 8 bits might end up getting to us, right? There's noise on the line, communication between two systems across a wired or wireless connection, the opportunity for noise, EM spikes, interference from other devices, your phone going off, that can cause data that is being sent to have that upper or lower bit threshold cross. And the way that bits work the computer systems typically is you have like a high voltage and low voltage. Low voltage would just mean it's a zero, and high voltage would just mean it's a one. So if you have something that disrupts the voltage such that it crosses the threshold for what we consider to be zero versus a one, we can misinterpret the message. All right, so anything that comes up as even parity, we'll read it as good, even though where's my strike through? Even though what we read was not good. Right, because the true good data here is 4 zeros followed by 4 ones. And in one example, we actually received 4 zeros and 4 ones. We actually properly received what was sent. One scenario, we found an odd parity, so we detected that this block of code is bad. So we can flag it as bad. Problem is, if we have an even number of bits to get flipped, right? So we had 2 zeros become a 1 here. Here we had 1 0 become a 1 and 1 1 become a 0. The parity still checks out. Right, so it's not going to work on its own. We just have a single parity bit. Right, so an even number of bits getting flipped will pass parity check, even though there is data corruption. Right, so depending on how much data corruption there is, we might have problems reading the data back, or we'll misinterpret what we're reading back, right? So if these were ASCII values in a character array, right, we'd have typos, bad characters in the data stream when we're trying to read up the data. Does that kind of make sense? Right, so the way we decide the parity bit, right, so we have the data that we want to add a parity bit to. If the number of on bits is even, we'll add a 0 parity bit. If the number of on bits is odd, we'll add a 1 parity bit. Right, so any of these that has an odd count of ones, we set parity bit to be 1. 0, yeah, yes, the count. However many on bits there are. Would the parity bit check be a secondary check? Now, parity bit is just going to be a foundation in some systems, but here we're going to talk about one that will make use of parity. Pull up the Wikipedia. Yeah, I knew that was going to come. That's why we need to log in. Get rid of the silly ad saying we want money. All right. Parity bit. That's not what I want. I want raid. Okay, this first one. I skipped right past it. All right. It's been around for a while. All right. Came from, I didn't realize it was a group of people. I knew it was a student project. Anyways, we're doing an array of inexpensive disks. Is, oops. one of the things that we'll make use of parity, not all. What systems would be? Well, we're going to talk about a few systems here that will make use of parity bits. Like Hamming code will be our more involved way of doing things. Okay, so redundant array of inexpensive disks. If I can type, which obviously I can't because spelling is an option there. So RAID 0, RAID 1, striping and mirroring. All right, these are common ways. So the RAID has a couple of objectives. One is uh, performance. We can get faster disk read and or write throughput with some of these RAIDs. And then the other one is data redundancy, basically a live backup. So RAID 1 is a mirror. So RAID 0 is purely performance, where they go ahead and split the data up across multiple. There should be an image here. If I mouse over this guy, maybe not. Open a new tab. All right, so here we have striping. So if we have, say, a file that is called A, and we break that file up into multiple pieces. So instead of just writing all of A to one disk, so we split up into 4 pages or whatever on one disk, we want to go ahead and read from that disk, read just one disk, so we're limited to that one disk speed. Alternatively, if we split that across 3 files, then we can read from all 3 disks at the same time, and the RAID controller can go ahead and splice the data back together, or depending on how we're doing the reading, mostly the writing will be faster, right? Because we only have to write, say this is 1 MB file, half a megabyte's being read here, quarter meg here, quarter meg here. All right, so it takes less time to write half a meg to one disk while we're concurrently writing a quarter meg to 2 other disks than it would to be just write it all to one disk. Mirroring, see if I can find, I can show me it there. Show me mirroring this one? I don't think so. Get a link. All right, mirroring is just making a copy. Don't have a good image on this one. But all right, 4 drives, A drive, B drive, C drive, D drive. Whenever you write to drive A, you write the exact same thing to drive C. When you write to drive B, yeah, write the exact same thing to drive D. So you could have a disk die on you, but the data is there because it's got a live backup. What is a disk in this case in terms of hardware? We're talking about a hard disk drive. All right, so we go on over to Newegg. Just picked up 3 drives recently, actually, because I'm gonna make a local cloud, and it will be RAID. Computers and storage. We're talking about where are my drives? Over here, hard drives. All right, one of these as our disks. All right, say we need 16 gigs, 16 gigs, 16 gigs. Funny thing, 16 terabytes of storage. All right, we can just buy one disk, dump all our photos, videos, what homework projects, whatever it is we want onto our one disk, hard disk drive. And everything's good. But 5 years later, 10 years later, hard disk drives, they don't last forever. And the more you use them, the faster they're going to die. It's mostly people don't have desktop computers for 5 to 10 years. So that's short of a lifespan for the hard disk drive usually isn't a problem because by the time the hard drives are about to die out, people typically will have a new machine by then anyways. And their old disk drive is 1 TB and say, it's too small. I don't want to deal with 1 TB drives. So they just copy it all over to the new system. So you don't have to worry about that. But if you do have a system like this for a long time or have bad luck and have a drive fail on you, now my current system doesn't have a RAID on it, but I guess 2 systems ago I did have, there was a 1.0 or a 0.1. It's mostly the same thing, but slightly different on how the stripes and mirrors are done. But computer booted up and was like, "Hey, one of your disks is dead. You should replace that." I'm like, oh, okay. And then a month later, I got around to replacing the disk. So I had a hard disk drive on me, but I did not have any data loss because right, it was just a mirror of stripes or a stripe of mirrors, whichever way it was. And tricky part is seeing if they still manufacture that same kind of disk to put a new one in its place. All right, so our objectives are performance and or data integrity. All right, so we had RAID 0, striping. You don't really need to know that for the test. RAID 1 is mirroring. So many common ways that things are done. We'll go back to our components. What are most motherboards have for a good long while. They support onboard RAID. We'll just grab this first one here. Let's see what levels. Usually 0, 1, and 1 plus 0. It's not RAID 10, it's 1 plus 0. That often call just RAID 10. Yeah, it's not mentioning RAID. There we are. All right, so RAID 0, RAID 1, and it says RAID 10 here, but that's just actually 1 plus 0. So you have mirrors plus stripes that you can go ahead and put on there. Ooh, got it for the NVMe SSDs. I'm going to be using existing hardware, so I'm not up to this point. I'm building a RAID system out here, but yeah, I've been wondering when they were going to get to it, and it looks like it is here. I don't consider myself a hardware guy. I'm only a hardware guy when I'm getting around the point where I'm going to build a new machine. Then I, get myself up to date on where things are technology wise, and then build from there based on the budget. But hard drives are pretty small when you're doing these NVMe's. Not that much bigger than a RAM chip. But anyways, getting your speed and performance. A couple of objectives, and when we get down to RAID 5, we're going to have parity. And RAID 4, I think RAID 5 is more common. All right, so if you're looking at any server farm out there, they're going to have RAIDs going on here. And this is where parity is going to come into play here. Get an underline on the parity. All right, so when writing to disk, here. Let's see, how can I get that back to normal text? All right. Writing to disk. RAID controller, which might be hardware or software. Splitting up the data into strips, stripes, however you want to call it. Also calculate the parity of those stripes against each other to write to the parity drive. All right, this one's saying it's distributed parity, so the parity's going in different places. I think RAID 4 has dedicated. This one has a dedicated parity drive. We have 2 parity disks. Lots of parity. And lots of these systems are going to be based off parity. When they have double parity, there's multiple drives taking care of things there. And so the basic idea here, if we do things as small as possible, disk 0 to disk 1, parity disk 0. All right, say we have the data as such. All right, so we have a file that we're writing disk, and we're just writing the first byte of the file to disk 0. Then we're going to write the second byte. I'm going to put here to disk. All right, so we're going to write these 2 bytes of data to disk. The first byte is going to be written to disk 0. Second byte written to disk 1. And then we'll just calculate the parity. The way we do that is we just look at each bit position. So we'll look at bit 0. We have a 0 and a 1. That's odd, and we want to make even parity, so I'll set the first bit to 1. And we'll look at the second bit in each of these. Those are both zeros. We'll just leave our bit 0 here. We have a 1 and a 0. So set it to a 1, 0, 0, set it to a 0, so on and so forth. We've got a 1, 1, so we leave it as a 0, 1, 0. So let's set that at 1, 0, 1's a 1, and 0, 0 is a 0. All right, so at this point, our data is distributed across multiple disks. So it took us less time to write to those disks. We did have to calculate parity as we were doing it. And we have data redundancy. If any of these disks die, the data can be restored, right? So obviously if the parity disk dies, it's easy to yank that disk out, drop a new disk in, run through the disk's data and recalculate parity, right? That's how we got the parity disk in the first place, is from the original data that was written to our data disks. If a single data disk dies, same thing, take the bad disk out, put a new disk in, it's going to be blank, and we'll go ahead and calculate parity based on other 2 disks, right? So let's say data disk 0 died, and this is the data that we're working with, right? So I have a 1 and a 1. In order for the data to have even parity, this data disk had to have a 0. I've got a 0 and a 0, so that had to be a 0. So on and so forth. Third bit is a 0, third bit's a 1, so this one had to be a 1. Fourth bit is a 0, fourth bit's a 0, so this had to be a 0. All right, and then we'll recover the data as we had before. But we are at risk while we're in that state, and the system could still be operational, right? Because the controller can calculate on the fly. Say I'm trying to read from the disk, because I can't read our data from our disk when the disk's dead outright, right? Not on its own, not without having to do the math gymnastics we're doing here to calculate the parity. So it can read just as it would do to rebuild the data disk. It can read from our 2 drives and then combine it together to bring out the actual chunk of the data if data is needed from this disk. Just depends on what's needed, right? Half of our data is on one disk, another half is on another disk, and we can have more than 2 disks. Data disk 0, data disk 1, data disk 2. All right, and our parity disk, right? Just as we did in our previous example, we can have as many bits that we want, and then calculate the parity. We could have a lot of disks and just solely rely on a single parity drive, but then you're getting an increased risk exposure to failure, right? Because if one disk just died, the odds of another disk dying are going to get higher, right? Because either we got a bad batch of disks or we're talking about a duration of time. It's been 1 to 6 years since this disk array was built, and we're reaching towards the end of life. So the probability of failure will increase as time goes on. All right. So we'll just go ahead and split the data. Obviously, the more disks we have, the faster it is to write to disk. Oops, they're not leaving up yet here. So we got 101, so that's a 0. 101, 100. Hold on a second. I'm trying to go too fast. 101. So that's a 0. And then we'll do it again. 0. Then we got 100 twice. And we got 010. It's 1. And we'll do that twice. And then we got 011. All right. All right. So in the above, red bit 0 from disk 0 and red bit 0 from disk 1. Calculate parity and write that to disk. Parity disk. Or bit 0 on that disk. Add data here, disambiguate. And with more disks, we're doing the same thing, just more of it. A bit 0 from data disk 0, bit 0 from data disk 1, and then we'll add in and bit 0 from data disk 2. Calculate the parity, and then write it to the parity disk. With the multiple parity systems, right, we're going to have additional redundancy. And the more redundancy we have, the more drives can fail before we're getting into critical mass. Let's see. So for example, 1, we'll get data 0 and data 1. From there, we'll calculate parity. Yeah. Example 1, 2 data disks. Example 2, we have 3 data disks.
Okay. Right. I was going to say,
Right.
well, like, sorry. So for example, in the test, we'll get like data disk 0 and then data disk 1, right? With like 0, 0, 10, 1, 1, 0, 0. And then we just need to calculate the priority disk. Is that right?
Yeah,
Or
calculate the parity bits. Yep.
okay. Yeah. Thank you. Sorry.
Mm-hmm. No, it's all good. All right, so striping alone is only performance and greater risk of data loss. Any drive dies, we're going to lose a lot of data. Mirroring gives us live backup, but we'll only have half the available space. All right, say we go to a smallest setup, 2 drives, two 2 terabyte drives, and it's mirroring. So that means every byte that's written to drive 0 is written to drive 1. That means you only actually have 2 terabytes of storage. Parity bit is a compromise between the two. We're losing space to be able to write parity drive. we'll get speed and data integrity or redundancy as a benefit. Right? If we had the first setup here, right? We had 6 terabytes of actual storage being allocated, right? 3 2 terabyte drives, 4 terabytes of actual data space being made available. Right, so we got 67%. We go 3 data disks, 1 parity, then we got 75%. Right, 6 usable out of the 8 total. Right, and you can read up on all the other situations here. Right, go. You're gonna be building your own. Right, you have just an asset, just multiple drives, and you would set these up as RAIDs. Right, so you have your local backup storage type thing, or just put all your shared important stuff straight to those in the first place. Right, it all depends on what you're trying to save. Having storage that's not on the machine itself is going to, I mean, it's slow because you have to wait to go across the wire. Even if you have a high speed local network, it's not going to get the speed of things as your local machine. But if all you're doing is playing a movie, right? It's like what, 4 kilobits or something like that for high def video. It's very low footprint of speed before you need to worry about network type translation there being not network throughput, slowing things down. So RAID systems are going to be leveraging parity very commonly. Not so much when there are only 2 disks, but usually you'll have systems with 4 being on the smaller side, but you can always go bigger. And those are all going to be based off of parity. Right, parity bits. Right, double check the Wikipedia. I guess I can toss the link up there. That'd be helpful. All right, same as here. Count of bits. If this number is even or odd, in fact, that's probably a good column to add to mine. Let's add that column to mine. And 0101 and 2. All right, so whenever this is an odd number, we will get that parity bit turned on. Right, and even parity versus odd parity is just inverse of the other. We're going to just do everything even parity. Even parity, just to keep things simple. Right, our error detection is going to be very, very limited. You can see we've got right here mentioned. See if there's anything else interesting. Nah, not at the moment. All right, let's dig up our Hamming code. It's going to have a nice big table down here. Where? This is also built on parity. What we're doing here is we're doing multiple parity bits. The purpose of this will be for error detection and correction. Error detection and correction. All right, so take a look. It's kind of small. Switch over here. The table here. we have multiple parity bits. We're going to have a parity bit 1, 2, 4, 8, 16. So we have 5 parity bits. That's going to be interleaved in the whole payload. And then all these Ds are going to be your data bits. So based off of our data bits, where they line up in this table, we will calculate the parity bits. So parity 1 is doing every other position. Parity 2 is doing groups of 2s. 2 on, 2 off, 2 on, 2 off. Parity 4, same idea, 4 on, 4 off, and so on and so forth. And the idea being that we have multiple parity bits covering any given data bit. Right, so we got 2 for data 1, 2 here, 2 here. Now we're up to 3 for data 4. Data 5 has 2, right? So 2 to 3 going to be the common situation here. However many bits are covering it. So flipping one bit, just like a single parity bit, will be detectable. Flipping an even number of bits, it's going to be detectable. It's covering a lot of situations where trying to flip the bits is going to cause our parity to capture what is going on. All right, so let's fill that out. We got 15. We'll do the 15 column. All right, so we got our index. And then we will have our data. All right, so we'll just do 4 ones, 4 zeros, pair of ones, pair of zeros, then we'll end up with 3 ones. All right, so parity 1 in the whole overall scheme. Right, data 1, data 2, data 4, data 5. So it's kind of concerning itself with these positions. Oh, they did data 1s here. Let me delete that column, add one to the right. Line up the number here. All right, so parity concerns itself. These particular positions, you do not need to memorize this. It's a little bit easier to see where things are when you look at the table all integrated together, but look at it this way as well. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9 bits of our data, and parity 2. Same idea. We're going to be covering various bits. 3, 4, 6, 7, so on and so forth. Now let's finish this row. 10, 11, and 13, 14. Do. All right, so let's max out. All right, so first row is position. Second row is one of the data columns. And then we will set our parity by bringing down data columns. All right, so we're going to have several rows here. That's our first parity bit. We want to calculate what is my parity. All right, column 1 here by looking at every other. So I want to know what is in its positions. So we will get our data. Get our data. Sorry, I'm going to hand myself here. Data is in position 3. We have 5, 6, 7, 5, 6, 7, 9 through 15. And then 17 through 20. So 0 and then 1, 1, 1. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so we have 15 bits of data. Parity bit cares about every other column here. So we're going to calculate parity based off of this data. All right, so we have 1, 2, 3, 4, 5 on bits. So we'll calculate the parity to be on. Really, it's like, let me just type, that's annoying. Or parity bit 1. Then we'll do similar things. We'll calculate parity bit 2. All right, so parity bit 2 is including itself in the pattern, just like parity bit 1 was. And then we have our first data point to go along with that. Skip 2, take 2. We'll skip 2, and we'll take 2. Skip 2, take 2. Skip 2, and then take 2. Right, so everything in the columns, if it's included, is going to be the same data point. And you'll notice that what we're selecting, things are not the same. There is overlap, and overlap is key to getting this to work. We want to overlap coverage on our bits, but the pattern is the same. Just count 1, 2, 3, 4, 5, 6 bits are on. So calculating our second parity bit, we'll leave that as a 0 to keep even parity. And we can move on. All right, so now we can do parity 3. All right, third parity bit. All right, takes up position 4 here, includes itself. And then 3 after that. Skip 4, take 4. All right, so position 4. Calculate what the parity is. Based off of the data, skip 4. And skip 4. And then we have 1 there at the end. All right, calculate before. We have 1, 2, 3, 4, 5, 6 bits on calculate the parity. And we will continue on there. All right, now we got our fourth parity bit at position 8. Now we've got 8 on, 8 off, so not much. Just skip this time around. All right, so we have 7 bits of data for parity 8. Add itself in there. We've got our 8th parity bit, or 8th bit for our payload. And that one will be even. And we can get down to our last one. All right, column 16. 0, 1, 1, 1. And we'll set that to a 1. Then at the end, right, copy all of our original data, and we can copy down our parity bits. And bold's kind of hard to see. Let's do underline. Copy our parity bits down. That's a funny looking 0. And another 0. And we got a 1 for that one. Right, and that's what the data would be sent. Send or write to disk. Wherever it is that we're sending the data. 3, 0, 1, 2, 3, 4, 1, 0, 1, and 0, 1, 1. Yeah. All right, so we had 15 bits data, 20-bit payload. There we go, say 33% overhead. As overhead makes sense. I had to add 5 bits on top of 15 to give us our 20 total. So we had 33% extra space required on top of the actual data that was being sent across the wire. Usually this is for things when sending data across the wire because that's where the most noise in the system is. Doesn't mean you can't have noise in our internal system, or you can have bad bits of memory, bad bits of RAM, bad bits of hard drive, where data that gets written to it is just simply corrupted. And usually we don't have things written in such a way that we're adding data integrity. There are the ECC, CC RAM, it should be error correcting code right in there, but that's beyond our scope here, so leave that alone. But again, just another system built on top of parity. Don't worry about trying to run through. I'm not going to give you a table and then ask you, what is P4, what is P1, anything like that. When I ask you parity questions, I'll give you the bits, and then you'll tell me what the parity is, type thing. If I ask you about Hamming code, right? Here's high level, how does it work, or what's it working with, right? Obviously, it's a parity-based error detection. Got the link. That's the rough idea for this one here. You think my kidding about anything at the moment? Right, obviously, just like many things in our course, been around for a good long time. Try not to get too heavily involved in here. Right? We're not going to get into the math side of things. Oh, looks like it actually is using ECC memory. Okay. Thought I was misremembering there for a second, but data errors will happen in the systems, and we need ways to try to protect. Not all RAM is ECC, but definitely things to take a look at. If you're digging into things deeper here, especially like the build your own machines, know what the different types of memory modules are and what they're doing. I'm forgetting, is a dual input memory module? I'm spacing on what DIM stands for now. Dual inline. Okay. Anyways, there will definitely be parity questions on the final. And RAID and Hamming code is pretty much just extensions of asking about parity on the final. Questions at the moment? No questions? We'll carry along. Look at a simpler repetition. Can be used to error detect and correct. We'll simply repeat the bits multiple times, and we'll use simple majority rules when decoding the message. All right, so encoding. We get two ways to encode a bit and repeat that bit, or we can encode a block and repeat that block. All right, so bit repetition here will take a bit and repeat it x times, where x, repeat it for a total of x times. Total of x times where x is 3. So start small. Data and encoded. Data 0 will encode 3 zeros. Data 1, encode 3 ones. So for data is 1, 1, 0, 0, we would encode 3 ones, 3 ones, 3 zeros, and 3 zeros. Or alternatively, looking at things in groups of ones or groups of threes instead of by nibbles. Same data, just representing it slightly differently. All right, 0, 0, 1, 1, 0, 0, 1. Right, however much data there is. We will just get crazy on repeating ourselves. All right, so decoding. Decoding with bit repetition. And we'll just take the same data. Right, so, and let's actually add in here encoded versus read. All right, so errors can happen. So if we get a bit flipped, in the payload. And so long as it's not too many, the majority rules will properly get us back to our original state. Right? Our original state was a 0. Original state was a 1. All right, same thing here. If we have our bigger data, we have the data a few times over. And I'm going to get rid of the delete redundant there. So let's flip some bits. Right, flip a bit, flip a bit, flip a bit. Leave that one alone. Flip a couple of bits here. We're going to have a problem there. A couple of bits. And we'll just flip all 3 bits right here. All right, so we decode this one. The first triplicate, 3 1 was encoded. 2 1s and a 0 made it through. 2 1s is the majority, so we'll leave it as a 1. 2 1s is the majority, 2 zeros is the majority, and 3 zeros is majority, is what we're decoding. All right, 0 1 1 0 1 1 1 0 and 1 1 0 0. All right, so 1 1 0 0 was correct. So this one we got correct. This one we got corrupted, but we don't know that it's corrupted. Corrupted and correct. All right, so repetition is going to be subject to errors if we have multiple bits flipped within a repeated block. We will not successfully recover. Encoding with block repetition. We use 4-bit blocks to just keep things small. Repeated 3 times. The same idea. So we have our data. We have it encoded. And we can try read and decode it as well. So if our data is 0 1 1 0. Right, let's take that block, write it 3 times. So depending on how much corruption we get here, where the corruption is, so I will just completely corrupt the first block, leave the second block alone, and I'll flip 1 bit over here in the third block. All right, so when we're decoding, it's just like when we were looking at the RAID, we're looking at the same bit position. In fact, let's color. All right, red becomes pink. Our dark filter. All right, so 0 0 1. So we're reading a 0 here, which is correct. So that's good. Even though one of those bits was corrupted. Then we will go move along to the next bit in each block. All right, so 0 1 1, read a 1. Which is correct, so that's good to go. And carrying along, move on to our next color. All right, 0 1 1, so we'll take a 1. Just a majority, and I'll leave, we'll color it. Might look strange to not be colored, I suppose. Go along green here. 3 zeros. We have a super majority on that one. So we're very much less concerned with, right? So again, it will depend on what bits. What bits get corrupted. Right, so let's, right, if I turn all these onto ones, we're going to see what's being highlighted there. All right, 0, 1, 1, right? So this time we have a misread, 0, 1, 1, so that's bits the same. Then we had a 0, 1, 1, so that's the same, and we had 0, 1, 0, so that's there. So we did get some corruption. And to the point where it wasn't corrected, right? That's not what I want to do. Right. When you have a simple algorithm, be it a simple hash function or a simple error detection scheme, simple tends to be limited in its capabilities and have to require at least a certain level of sophistication in order for things to work well in a greater number of circumstances than our simpler solutions do things. Am I going by placement, like the first bit of each block? Yes, based on the placement. Right, so the colors, the position, each bit is being matched up for our majority rules. As those positions is what is being repeated. Remember, our original data was 0, 1, 1, 0. So this 0 is what is being repeated 3 times. And then this 1, the first one, is our second position being repeated. Next one, third position being repeated. Right, so we would read 3 blocks, however big a block is that we're sending, and then we will go ahead and reconstruct that block from the 3. And so basically like taking a tree, right, branching it out triple time, and then merging them back together. Hmm. Let's see. Test 5, which is next week. Let's talk about test 5. Coming the wrong way here. Do, 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 do. Test 5. Shift folding. Let's get our fancy calculator out. All right, do some fun math. 698 plus 741 plus 253. No, I didn't type those numbers in right. Let's try that again. 698, 741, 2. Okay, I forget to put the plus symbols. 698 plus 741 plus 253. All right, gives our fun hash value. Perfect hash. All right, let's get modulo, or rather division modulo. Then we've got modulo plus. Let's just the other way around. Modulo division, modulo plus division, and then modulo minus division. And then we have our various keys. 6, 32, 33, and 44. Because we're looking at the hash value. Remember the result of a hash function is a hash value. There's no hash table yet involved. If we're then asking what's the normalized index, then we would need to modulo it to get to fit into a table. Otherwise, a hash value is going to be a raw chunk of data. Which remember like when we did our MD5 and things like that, you give it a key and it makes a big old massive value from the key. All right. 10, size 10, keep the math simple. 6 divided by 10 has a remainder of 6 and divide 0 times. 6 plus 0 is 6. 6 minus 0 is also 6. 32 modulo 10, 2 and a 3. 5, -1, aka 9. So we have a wraparound. But unless things actually add to it, don't really need to do the wraparound part. Leaving it as -1 will be fine for the purposes of the question. Modulo, adding, subtracting. Modulo, adding, subtracting. All right, so we have duplicates in the divide column. Duplicates. So divide does not give us. Go to cache. Duplicates. Here, duplicates here, right? Modulo, nice and unique distribution there, which means constant time operations. Bear with me here in this question. All right, carry along. 40 normalizes to 2, collision. We are using linear probing. So we'll just go ahead and go down to index 3 there. 60, collision, wrap around, gives us the index 2. Some reasonably, yeah. Linear probing. Garbage collection. When does C come back? All right. So we have object C being tracked by X after line 1. And then we have line 2, Y is also tracking object C. We have line 3, Y goes along, tracked object B. And then X leaves C after line 4. So line 4, object C will be reclaimed. Best fit, 42 bytes, right? So 50 works, 40 does not, 32 does not, 1000 works, 1000 is not the best fit, so 50 will be our answer there on white space. Question for whatever reason? Garbage collection. All right. We have black set, gray set, white set. Gray are A and G to start. Leaves everybody else. B, C, D, E, F, H, white. All right. A needs to move B and C over. Where to go in the black set? G has no one to move over. B has no one to move over. C has E to move over. E has no one to move over. So we have D, F, and H. D, F, H as our garbage. All right, so we're going to have the hash function. Calculates the hash value with a key. And I'll have a lookup. Takes a key and returns back value for that key if it exists. And we're having an add function. Takes a key value and adds it to the table. We're going to have some sort of probe resolving collisions and some sort of probe lookup. All right. Handles collisions and lookup. And a delete function. Removes a key and its value from the table. And then probably helper function. Delete helper. Takes care of vacancy and finding the key if there was a collision. Right, base code, much like you've done in your labs. Let's see. Just put 0 points there that way. Gives me a nice 100%. All right, garbage collection, memory management. Various hashing, probably half the test. Let's make sure you're good on hashing. Logic for question 2. All right, so we're looking for perfect hashes. So we just want to we just do key modulo 10. So 6 divided by 10 equals 0. 2 divided by 10 equals 3. 3 divided by 10 equals 3. And we can stop here. We failed. Perfection. Perfection. So we move along to the next one. 6 mod 10 equals 6. 32 mod 10 equals 2. 3 mod 10 equals 3. 4 mod 10 equals 4. Perfect hash. And since this is a multiple choice one, there's not all that apply. I can go ahead and stop answering the question at this point. Because we have found our answer. This is our hash function that we want to use for this particular set of data to give us our perfect hash. Is this a minimally perfect hash? Our table with 10 elements and 0 collisions. Yes or no question, or yes or no answer to the question. Do we have a minimal perfect hash for this hash table? Feel free to guess. Toss your answer in the chat. Doesn't hurt you one way or the other. I've got one yes. Everyone agrees. There's anyone dissent? Got a couple of yeses. What was or what is a minimal perfect hash. We've got the perfect part. There are no collisions. What makes a perfect hash become a minimal perfect hash? Right? Yes, the least amount of size, the smallest table big enough to hold all of our elements. This table has 10 elements in it, which means we're wasting space, so it's not a minimal perfect hash. We would have to create a table of 4 elements, then look to see if any of these would actually give us a perfect hash, in which case we may not have any of these be it, and we would get none of these for the answer. Yep, we would need the hash values all end up being 0, 1, 2, and 3 after being normalized into the table. Yeah, it's a perfect hash, but not a minimal perfect hash. All right, so we can take it. So try to make it minimal. Table size is now 4. All right, so we have 6 divided by 4. So it's a 1. 32 divided by 4 is 0. And then we've got 33 divided by 4 equals a 1. So stop. No longer perfect at that point. Really? Doesn't want to resize. Okay. Just hit the enter then. All right. 6 mod 4 equals 2. 32 mod 4 equals 0. 3 mod 4 equals 1. And then we have 44 mod 4 equals 0. All right. So we got a collision there. We need it to land on a 3. Right, so if it was a 35 instead of a 44, we would have had a minimal perfect. And then we could continue on testing the other ones to see if we have our minimal perfect hash. Other ways this question could be asked, we do the reverse. Given hash function x, give me y values. That would be a perfect hash type thing. You know, like 0, 1, 2, 3, 4 type thing. It's not terribly difficult to answer that particular perspective. Let's add additional constraints on the values, but all right, someone was asking about number 3. Let's see. What was the question about number 3? Go through 3 and 4 again. Okay. Number 3, we have 40 being added to the table. 40 wants to go to index 2 per whatever hash function we're using. And your probing says go down 1, and then we'll insert it there. 60 says it wants to go here after its normalized hash value. That's a collision, so we will try 0, collision, try 1, collision, and then we will find 2 is available and write it there. Number 7 in the notes, tricolor, so garbage collection. Garbage collection. Tricolor. 5.5. Right, you'll be given the various objects. You'll be told who the roots are. And then from there, we'll start moving things through our sets. Right, we had A and D here. And A got pulled out, leaving D alone. D got pulled out, but that required E and F to move out of the set, so on and so forth. Question 1 again. Numero uno. All right, so we have fold lengths of 3. So take 3 digits out, take 3 digits out, take 3 digits out. Add those together. And get our hash value. All right, if there was additional, so let's say we had length 4. Yeah, we'll do length 2. All right, putting a 0 in the front does not change the value of our number. Then we're going to add that together. All right, so we'll 0 pad on the left side because that doesn't change the number that we are hashing. Then we can go ahead and chop it up there, and it gives us nice even lengths. Right? So that was a pad left. We could have padded right as well. Right? We talked about both ways. We just take the number, add one at the end there, because basically take the number, right? We just grab 2, grab 2, grab 2, grab 2. One's left over. Right? You just leave the 3 alone there, and not even bother padding it, and just add it all up. Right? They will be on the test even because it's simple. Right? Which way we handle things here is it's more or less arbitrary when we have uneven splits. There's lots of ways we can handle it in one way versus the other. It doesn't really much matter so long as the same functions being used on during the lifetime of a hash table. We will be able to properly add and look up and delete items from the table with no problem because consistency within itself is all that is necessary. And for the test, we will use the simplest form for the folding. The length that we're using will be a factor for the length of the key. Yeah, so length 4, we do 2 ways where we 0 pad, 3 zeros at the front, so we have 6 plus 9874 plus 1253. Or the other way where we just go and just start grabbing. Grab 4, take that as value, grab 4, take that as value, grab 1. Okay, that's our value. Yeah, test 5 is 5x in the notes. The whiteboard, rather. Next week. So, all right. So next week, here we are on the 4th. Yes, the 4th. We got the test. Got test 5. Got over test 5. And we have review for the final. Yes, the final will be the week after that. And go over the practice test. I don't know why it's showing practice test final and final exam practice here. I haven't dug into that yet to find why there's two things popping up here. Unauthorized. Well, okay, linked to something that just doesn't exist. Practice test final. No, there's not even I don't know where it's getting it. Canvas is weird sometimes when you copy the course from previous iteration. But yeah, we should. We'll double check. Double check. Make sure that we haven't forgotten anything. Work our way backwards. Extra Hamming code, rate, parity, Huffman, we talked about that. And memory allocation, compaction, tricolor, all that fun stuff. We talked about backtracking, right? Did we talk about ink queens? Should have. I forget, it's been a while now. Yes, we'll talk about that tonight. It's just basically problem solving. Oh, yeah, all right. So let's go and take a 5-minute break. Then we will talk about N queens. And then I believe people have questions about program 4. Just due in 3 days. We'll also talk about that after a break. But yes, after N queens, we should be wrapped up on materials for the course. This next week is test, review for the final, and then go over the test 5. Final is cumulative, as mentioned earlier tonight. Right. O-notation, linear search, binary search, all stacks, queues, all that relatively easy stuff coming up to graphs, trees, hash tables, and everything that'll be in test 5. Yeah, so the final is basically like take half the questions or a third of the questions from each of the previous tests, use different numbers in the case where numbers are involved, returns which of these are to which of these aren't type things with multiple choice, multi-answer questions. And then there's the few items from section 6 from the whiteboard that we've not been tested on that we will be tested on the final, but that's like 10% of the final type thing. The final is twice as big. It's a 2-hour and 10-minute test. It's I don't know how many questions there'll be, but typically twice the number of questions, 50, 60 range. Tends to be a little bit more multiple choice. The code on the final is reading code. If there's any writing code, that would fall under the extra credit bucket of things. No, the different methods of folding, you should generally expect a different result in the values because you're chopping it differently. Right? It's like taking a steak and chopping it with the muscle fibers or chopping it against the muscle fibers, right? You still get bits of steak in the end there, but it's going to be a different result. Both shapes and size and the smoothness of the cuts. Okay, so let's take 5. We'll come back at 22. All right, backtracking. Nothing terribly exciting here. Is when you do dead end or solution, and then work your way backwards. And attempt an alternative path. It's a typical common way to solve for a maze, right? Exploring a maze. You have three ways to choose from. You can go left, right, or straight at a particular intersection. Chose to go left, that led you to a dead end. You come back, and then you choose straight from the original perspective as the alternate path type thing. So with n queens, this is a board in size n by n, where we are attempting place n queens on the board such that no queen can capture any other. All right, so if you remember, or you never played chess, queen can move any distance in horizontal, vertical, or diagonal directions. All right, so we can do a one board. And it's just a triangle. And oops. All right, a board of one queen. And so one board is solvable. A board that's 2 by 2, it's impossible to solve because the queen can take all three of the positions. As such, no solution can be created with that board. We have the same problem with the 3 by 3. Right? We effectively just go column by column as we're solving it, because placing a queen in a column eliminates the queen from being able to place in any other position in the column. But let's see if we can solve a 3 by 3. Drop a queen in the first option. Second column, cannot place here because the queen can take. Right, and we'll just go ahead and X out all the positions. Second position doesn't work. Drop a queen there, which can take that position. So we've run into a dead end. There is no place for which the queen can be placed on the board, having placed this queen here. So what we'll do is we will backtrack. Let's see how well that works. That did not work well at all. All right, so we will take the queen off the board where we just placed it. In fact, and there was no other option for the second column, so we're going to go all the way back to the beginning and pick that queen up off the board. A little bit too much there. All right, so we backtracked to our first, all the way back to our first decision. Decided that that wasn't a good decision. And we go ahead and place the queen down in the second position in the first column. And that immediately locks out the second column, so that was not a good decision. We'll pick that up, repeat, and then we'll hit the mirror case this one, which there was no solution, so there will also be no solution there. So what we'll do is we'll go bigger to a 4 board, which is the first practical point in which this is relevant. And I just, yeah, there's a way to say clear text. Yeah, whatever. Probably not. All right, a board that's 4 by 4. I won't bother Xing out the column that we're in because we're not going to be able to try. No point in even bother trying. I can try to place it here, be like, nope, I can catch. Nope, nope, nope. So, second column, first 2 positions are blocked out. So I'll start blocking out additional positions in the next, and we can see we've run into a dead end. So that didn't work, so we can pick that queen up, unmake that decision, and try the queen in a different position. And that gives us an opportunity to drop the queen here in the third column, but she then completes the blocking for the fourth column, so we've hit a dead end. So we are going to roll back all the way to our first decision. And let's move along to a new drawing. Yeah, we'll have 1 queen in each column, 1 queen in each row. It's the only possible way to have n queens on the board and not capture each other, so it's the diagonals that we are dancing around. Right, so this queen did not work there. And it didn't work all the way up there either. So let's backtrack. Right, so we've picked up the first corner, dropped the queen in the next available position in this column. That knocks out a few positions in the table that we can no longer occupy. We still have a place in the second column. We have a place in the third column. And we get to our first solution. One of 2 that there will exist in this 4 by 4 board, this position and its mirror. All right, we'll just X things out here to make it complete. And so that's one of our solutions, and then we'll have a mirror. We would backtrack. Right, so now we found our solution, we go and start backtracking. Look to see if there's another place that the queen could be placed in this particular column. There isn't, so we would backtrack. And then we'd see there's nowhere else here, no, it's here, and we'd backtrack all the way back to the beginning. And then we would get the queen into its third row, and then we will get our mirror solution. As our second and final answer. And we'll use backtracking. Then we can grow from here. Go to a 5 by 5 board. Look to see where we can place the queens. The number of solutions grows very, very quickly. It'll take seconds to find all the solutions, and the boards are small. That's way back 20 years ago. When I wrote a program to solve it, it's not terribly difficult to write the program. You just gotta drop pieces on the board, increment the counter. If we're gonna actually solve this, Q would put 1. Number of queens that can take any particular position. Every time you drop a queen, just increment the counts for all the places that they can take. That way, when you're picking up, you just do the reverse, you decrement. And if position has 0 in it, then we can place a queen there. Right? Drop our queen down here, increment all the positions. Yeah. That she can capture. That's not a 2. And diagonals, diagonals, diagonals. Don't forget about the diagonals. All right, drop a queen down. All right, do our incrementing, drop the queen down. Right, and we'll get down to our first solution, a 5x5, and there will be many of them. You read about them. You read about how many unique ones and or solutions with and without mirrors type things. Read about that. But yeah, so 20 years ago, I think I got to a board that was 21 by 21 in size with the application running overnight. So you're like, just tell it to run, go away with the computer, come back the next day and see how far it got. So, oh, we got to 21. Checking along the ways there. Okay, we getting half an hour. Really? That's it? That's as far as we get in a half an hour. Of course, we're talking about probably a 200 megahertz laptop computer 20 years ago. So we can get a lot further these days now that we're operating the gigahertz spectrum of processing speed. Plus, we got multiple cores. We can start feeding work to each core in the system and really start cranking through the solutions. This is one of our NP problems, just like we have with the traveling salesperson. Number of possible solutions as the problem set grows even just marginally. It grows so fast that there effectively isn't a good solution to the problem. It's easy to find a board of any given size that has a solution, assuming it's a board of size 2 or 3. Because 2 and 3 don't have a solution, but 4 and above have solutions, and the number of solutions grows. Right, let's pop. Should be table here somewhere. There we are. Right, no solutions. Board size 2 or 3. One solution's 4, 2 accounting for mirrors. Right, 5 has 2 solutions that are distinct. 10 when accounting for mirrors, but then right, the problem set dips at 6 for whatever reason, but then keeps on right getting up to 20. We're getting the millions quite quickly here. Billions, just a few rows after that, and trillions, just a few rows after that. Right, fun. Mentioned backtracking in here. There we go. Grab that link, grab the other. Do. Drop the links and get our end queens. 6.8. Right, the goal is to get n queens positioned onto the chessboard, right? So that no queen can capture any other. And that's what these numbers are representing, is how many queens can capture that position. So I can move this queen into any of these positions, and if there's another piece in that position, that piece would be captured. Okay, the whole objective of chess is to capture the opposing team's king, and you do so by positioning your pieces and capturing the other team's pieces as you go. All right, so going back to the timeline, the review that is next week for the final, that is the week following, is you asking questions. How is a queue different from a stack, or whatever it is we want to talk about? Right, we're not just going to try to reiterate through the entire semester over an hour or two time frame. Go through your notes, see what's fallen off the top of your head, and ask about it so we can talk about it again. Get it back into the forefront of the mind and more easily applied onto the test. Yeah, semester speedrun, right? We do data structures for dummies in 2 hours. One of the Sam's teach yourself whatever in 24 hours type thing. I wonder if anyone's ever actually clocked themselves attempting to learn the subject by one of those 24-hour books and see how many hours actually elapsed. And we had about 40-ish hours of lecture time ourselves in this class, just going through this materials, and we were really only making a gouge into the surface of data structures. There's quite a bit more out there. More of what's out there is a little bit more specialized. Right? Hash tables, stacks, queues, used quite commonly. Graphs have their application domains, especially talking about networking and pathfinding. Right? You're doing AI stuff for computer-driven mobs, and they're trying to get from point A to point B. That's basically they're running a maze effectively because there are obstacles, rivers, bridges, buildings, whatever structures that are there, and they have to get around them. But that's the end of that. So, what questions about program 4 do we have at the moment?
I think you already kind of, well, I asked this in Discord and you kind of answered, but I still don't really get it. Um, it's about like when we were, what is it, to support operators plus, minus, divide, multiply, mod, and exponents. Um, I'm just a bit confused because like in the example you have, what is it, like print full mirror times two. Like are we gonna have, are you gonna test this with like just regular value variable times like regular integers and then that being saved? Because I'm
Yeah,
going over your inputs, and bone mirror times two isn't saved. So
no,
that's
yeah.
just where, yeah.
If you just print it out, we're not changing the value. There's no
Right.
assignment operator, then there's no change in the value.
But if would you are we gonna test with like Bomir times two is equal to something and then that like saves a value, or?
No, it just prints it out. So there should be a print statement
Yeah, I
involved
know
in that
there's
one.
I know there's a print statement. I'm just asking like would you like do would you test the code for it to not have a print statement and it's being saved is what I'm asking.
No, assignment, right? So assignment, program. Yeah, so you'd have to, if there has to be an assignment operator that changes the value of the variable unless it's a unary operator, which changes the value of the variable. Right, so let's say we do x plus plus. And we do x plus 1 type thing. uh, so let's say we have our program here. All right, class hash table. And I'm just going to have it everything. Yep. I'm going to cheat in my example here to keep things moving along. Gonna do variables. And okay. All right, so we're going to have a collection of lines that we're reading from the screen. I'm just dumping them into an array so we can work on them. We're going to use string stream or something along those lines to break the line apart. I'm using C# here for my example just to show the process. So that part would change. All right. So if switch and whatever if. We'll just leave it that way. No, do switch. Ahead of myself here. All right. Stupid background compiler here's distracting me with its non-errors. All right, we're gonna have a case for the various keywords in the language. All right, we got prints, we got com, start, finish, etc. All right, so in the case of var, all right, its length. All right, so if we have four, all right, this array of var x equals one sort of scenario, there's four pieces on the line, in which case we'll get the value out. From that bit, and then we'll add whatever the value is into our table. That was interesting. Okay. Always important, semicolons. And we'll add to our table whatever our key is, which would be parts one, and the value to our table. And then we get along to print. Same idea here is let's see. Get the line by 0. That's fine. Print will have similar idea. We have a couple of cases. We have print x. Right, so the parts length is equal to 2. Just a matter of dumping out the console. Sub 1 is plus table. Look up part sub 1. All right, let's see what we got here at the moment. See how broken it is. Missing square brackets. Okay, let's get that put in there. Line 12. Probably can't do that. Using the right version here. Okay. All right, so we've got x is 5, x is 5. All right, so we declared x, set to 5, we printed it. Don't have increment implemented my default branch to handle variable statements on their own. And then I said x is 5 again, and we haven't handled this part where we're doing the math. So we can do if the length is equal to 4, we're going to have to do more logic here. All right, now we need to look to see who is a variable. Int left-hand side and right-hand side. Parts. All right, so this one is print x plus 2 type thing. Or print 2 plus x. Or print x. Whatever the operator is, which is using plus as the example. All right, so parts 1 and 3. If we can't parse out left-hand side, it's not a number, in which case we need to get, means if it's either a number or it's a variable, right? So we have two scenarios. It is a variable or it is a number, right? So if I can string stream it into, right, use the extraction operator from a string stream into a number, then that's the value of the left-hand side. If it's not, we just need to look it up. Look up. This supposed to be parts 1, not parts 3. It's 1. And similar idea for the right-hand side. If parts 3 is a number, we're good to go. Otherwise, we'll grab it from our table. And then it's a matter of what is the operation. All right, so result equals 0, switch on parts 2 is either a plus. Oh, it helps to have the other double quotes there. Or it's one of our other operators. Right, we have addition, subtraction, multiplication, division, modulo, and exponentiation. Is that right? And result equals left-hand side plus right-hand side. Copy paste, change my operators. Add, subtract, multiply, divide, modulo, Add in a math library so I can do exponentiation. Exponent. No, power, whatever it is. Math function. I'm just going to cheat and say it's 100. It's be much better as a function, so we don't have this massive switch here, but we're being brief. All right, so this should probably handle the x plus 1 situation now. Falling out. Well, it seems to be mad at me here. Let's abstract that to a function. That's what my problem was, missing a curly brace. And now that we have it, we can print it out. Parts. One. Plus parts sub 2. Let's keep the whole thing there. Parts 3 equal to result. Okay. Let's test see how well that's working. I didn't need to say that. Okay. Anyways, get my library squared here, right? So we got x plus 1 equals 6. We're handling our math stuff there, so we can do some extra testing here. Get a few more x. Let's swap things around here. Multiplication and do division there. All integers, just doing integer math. My example should just be using integers. That's the idea there. Increments. So the default or your else if whatever means parts sub 0 is the variable. All right, so if parts length is equal to 2, if I can type length, right, that means we have x plus plus type thing. All right, so we can just switch parts of 1 to either plus plus or it's minus minus as far as our happy path is concerned. Beyond that, we're not concerned. I don't have an update here, but we would get equals table lookup parts sub 0, get our value, right? Value plus plus, value minus minus, and our switch, and then we have table update. All right, sub 0 and our updated value type thing. So I'm going to add an update function. Okay, and value. Where this, of course, will be linked lists and all that, array of linked lists and all the other things there. I'm just saving the time writing that part because mostly I presume we care about the interpreter. All right, we've pulled it in for the unary operations. Let's see what we broke. Oh, it's mad because I used value again. All right. So value is already here. I don't need to redeclare it. Just reuse as is. All right, so we had x equals 5. We incremented it to 6, and then all other expressions changed. All right, so all of that code is tested, which means we can start adding more to the language. All right, we need logic in here, or, I try to pull a value for a variable, and that variable does not exist. We want to have logic in there. Make sure it does exist. All right, one of the things we can do here is like it is exists. And if it has it, we know we can do things here. So I've been pretty much optimistic at the moment here for doing things, but we want to fold that in. All right, where we're doing lookups here blindly. We shouldn't be doing those blindly. We should make sure that it has the value. It has the key. Over here, looking parts sub 1, for example, but logic in there, so we can say print undeclared variable. Otherwise, we have right? If the length is greater, why can't I type length tonight? All right, so we have x equals x plus y or something like that. All right, so we have 1, 2, 3, 4, 5. Should be our other scenario. We have similar logic right above. Figure out what part. Parts 3 and parts 5 are. And here we do our test here. If not, table as key, parts 3. I'll put our message. Does not exist, whatever our message is. And else if doesn't have right, 0, 1, 2, 0, 1, 2, 3, 4. Get my numbers right here. 2 and 4. That doesn't exist. Well, do I have left hand side, right hand side defined here? So I don't jump the gun a little bit there. Do. Not. Parts 2 LHS. It's not a number and it's not in the table. Then we got problems with it. Same thing, right hand side. Parts 4, right hand side. And we got our else. We'll do that in a minute here. First, we're going to have a couple of bad ones. X divided by Y, right? That should complain. That doesn't exist. And if I flip that around, oh, just bail on the Y. So I get to the point where it's complaining about the Z not existing. Slash does not exist. I have a typo there. Do. Parts to, there we go. Right, Y does not exist. Right, and the logic. And more than just this way. I didn't break things up at all here. Much better if I was breaking these things up. Right, have an interpreter class. And that deals with all the jazz. As a hash table. As a field. As helper functions. For each keyword. And any other functions. As is needed. Call it once per line, or however you want to interface with it. That's a general idea of things. Other questions? Any questions about anything else? Why is the square root of -1i? Why not? Yeah, because expressions are just going to be binary and binary arithmetic or variable names, right? Names, plural. Right, I should be able to adjust mine here. It's not handling it yet. Go over to the lab. Let's do tomorrow. Sure. What's our questions there? Run length encoding.